Okay, so this is 11.1 orthogonal functions. We're going to start off with the definition. So we're going to start off with the definition, and we have two functions on the interval AB, and the inner product of the two functions, f1, f2, is defined as, this is the inner product, and it's the multiplication of the two functions from the integral of a to b. Here's an example. So the inner product of sine of x times cosine of x is the product of those two functions on the interval from 0 to 2. So we are going to have to do a u sub. Doesn't matter which one we pick because they're both the power of 1. But of course this will be easier because it's a positive derivative. But let's go ahead and plug our limits of integration in there since it's du now. So 0 sine of 0 is 0. But when we plug in pi over 2, the sine of pi over 2 is 1. So the inner product is 1/2. So another definition is if we have the inner product of two functions as 0, then those functions are orthogonal on AB. So, it doesn't really mean perpendicular graphically. So it's just a definition that they are orthogonal if their inner product is 0. So my note here is just what I just said before. It does not have the same geometric connection to perpendicular vectors. Let's do an example. So we want to show cosine of x and cosine of 2x are orthogonal on the interval minus pi to pi. So we do the inner product, which is the definition from minus pi to pi of the product of those two functions. Looks like we'll have to use a substitution. You can use the double angle. And I know there's 3 of them to choose from. I think we'll use this one. Oh, I just realized I got this property wrong. This is 1 minus 2. That's the property of the double angle. So there's a 2 there, and a 2 there, and a 2 there. This is going to be sine of pi, and then minus sine of negative pi. They're both 0. This is 0. But when we plug in here, change the limits of integration, looks like it's going to be from, we plug in minus pi, sine of minus pi is 0, and pi is 0. So basically, this is just 2 times 0, which is 0. So the inner product is 0. Therefore, Those two functions are orthogonal. Therefore, are orthogonal by definition, since their inner product is 0. Here's another definition. Okay, so the norm of a function is the square root of the inner product. And it's kind of messy to write the square root of an integral. So what we like to do is the norm squared, f squared, is the inner product, which is the function squared, the integral of the function squared. Just makes things easier. And then if you're looking for the norm, then you take the square root of that. Let's do an example. So the norm of cosine of mx on the interval, by definition, by the power reducing formula, so we found the magnitude squared. So therefore, the magnitude is the square root of pi. So the set actually goes on and doesn't end. It's an infinite set. So here's our definition. We have a set of functions phi I, which is phi 1, phi 2, all the way to forever, is orthogonal if the inner product of each of them, so the set is an orthogonal if the inner product of each of them is equal to 0, as long as they're not the same function. So they're different. Let's look at an example. So we have a set here that is orthogonal on minus pi to pi. We're going to verify this. So the first thing to verify is this times this times this, the first two are 0. The inner product of any of the two that are not equal are 0. So we'll start off. This is sine of x from minus pi to pi. So we get 0. And then any other two, these two or these two. So this will be the formula, the product of sum. The product of sum is half the cosine of m plus n of x plus the difference of the angles. M minus n of x dx from minus pi to pi. This is equal to half divided by the angle, and all of this is from minus pi to pi. When we plug in pi here and here, we can see sine of whatever, and those are integers. We will have half 0 plus 0, which is 0. And we can also see if m does equal to n, it is undefined. So we're only talking about when m doesn't equal to n, the inner product of all the different, when these are all different, the m's and m's. Here's another definition. So phi I, infinite set, is orthonormal, not just orthogonal, but orthonormal. So we have that it's equal to 0 if they're not equal. But we also have, so that's orthogonal, that definition right there. But when we have the inner product is equal to 1 when they're equal, so the inner product of each of them with themselves is equal to 1. Oops, when I is equal to j, when they're equal. Means, i.e., the magnitude of each one is 1. So here's an example. So we showed this example is already orthogonal. So let's write that. On minus pi to pi. So the question about the set is, can we build an orthonormal set? They're already orthogonal. Can we make them each normal? Yes, of course we can. Why would I ask that if we couldn't? So how do we do it? All we have to do is we divide each of them by the norm to make each of them normal. So we divide each by the norm, their norm. So for that particular set, let's find the norm of each. So for the first one, it's 1. Let's find the norm of 1. It's the integral, we take the square of it, from minus pi to pi. That's our set. It's given, which is x. It's 2 pi. So the norm, 1, is the square root of 2 pi. That's our first one. All the others is the magnitude of mx. M could be 1, 2, 3, forever. Didn't we already do that one already? Oh, wow, look at here. The magnitude here, and it was the same integral from minus pi to pi. It's the square root of pi, so we don't have to do that again. And I'll write from above. We'll box it. So our set, our orthonormal set, is 1 over the square root of 2 pi cosine of mx over square root of pi. So our question is, why do we care about making an orthonormal set? So the answer is orthonormal functions can form, so they can form a basis for a function space, which is actually extremely cool. Let's look at an example. We have two vectors. Let's go ahead and take the inner product of those two vectors. And our inner product is the actual inner product. It's 2 times 1. It's the inner product of two vectors. 2 times 1 plus 1 times minus 2. So our inner product of these two vectors is 0. They're orthogonal. So now can we make an orthonormal set? Sure. We take the magnitude of V1, which is 2 squared plus 1 squared, square root of 5. Go ahead and take the magnitude of V2. We divide by the magnitude, but they're both square root of 5, so it's 2i. So divide by square root of 5. And so there we have it. So now U1, U2 is an orthonormal basis for R2. What does this mean? Any vector in RT can be written as a linear combination of U1 and U2. So in general, we're going to let B our orthonormal bases. So a linear combination means if V is AB, any V in R2 can be written as a linear combination of U1 and U2. Again, this is any vector. V is any vector in R2. Then what we have, if we take the dot product of U1 times V, we get U1. V is our linear combination here. We can distribute that. That's a vector, so it's C1, U1 dot U1 plus C2, U1 dot U2. Well, we do know, since it's an orthonormal set, this is 0, and the inner product is 1. So what do we get? We get C1 times 1 plus C2 times 0. This is 0, we get C1. So we have C1 equals the inner product, the dot product of this, which is VU1. The order doesn't matter there. Well, we do the same thing, and we get C2 equals U2 dot V, which is V dot U2. Put it all together. And V, this is actually the projection theorem. Any vector V in R2 is C1, which is VU1 times U1, that's my C1, plus VU2 times my U2. Again, this is my C1, this is my C2. It's a linear combination. So let's keep going with it. Let's pick a random example here. Let's say V is 3i minus 7j. We write that as a linear combination. So we're using the above example still. Or we just write it out. C1 and C2. Writing this out. So the dot product, V, this is V. So our V, and then our inner product with U1. Remember, U1 is right here. So dot product with U1. Okay, so these are the inner products, which will give us a scalar. So let's work this out. And this dot product times that last vector. So this is our scalar. 6 minus 7 is minus 1 of these. 3 plus 14 is 17 of these. Distribute, distribute, add your i's and j's. Add our i's, add our j's. And let's multiply that a little bit better. That times that is 1, which, if you remember, this checks out. So you can see that that formula works. That's the end of this video. We'll be doing the Fourier series in the next video.